Okay, let's get started. A couple of administrative things. First, a reminder that problem set 7 is due Tuesday in 5 days. Second of all, I'd like to go ahead and return problem set 6. So let me pass that around. It should be in alphabetical order as usual. Let's see. Questions about administrative stuff? Okay, let's go ahead and get started then. I'd like to begin today with a quote from Thomas Edison in 1931. He says, "I put my money on the sun and solar energy. What a source of power! I hope we don't have to wait until oil and coal run out before we tackle that." You can see why he's one of the great American inventors. Okay, so Edison has something to say about oil and coal and solar energy. I'm going to start today by talking a little bit more about global oil supply. So here's a table that I'll refer back to. It's exactly the same table we used last time to compute estimates of these technology parameters for country supply functions for oil. So I'd like to sort of dwell on that problem just a little bit longer. Okay. Okay. So this is all just a complete review, I think. This is all material from last time. I just want to put it up here so you guys can have it handy to refer to. So the basic arrangement is this. We were imagining a production function that looked like this for a firm or for a country. And recall that this BI was some sort of technological parameter. There was this labor and capital in the usual way. There's also a stock of the resource, which the firm or the country takes as given. We thought we sort of related that to oil reserves. Let me ask you a question. Looking at this production function, does it exhibit constant, increasing, or decreasing returns? Okay, so Chris, I heard the word constant. So Chris, why do you say it exhibits constant returns to scale? Okay, so from one point of view, this looks like a production function that has constant returns to scale because it's Cobb-Douglas. And if we add up the parameters here, alpha plus beta plus 1 minus alpha minus beta, by construction that sums to 1. So what that tells us, if we were able to take this technology and double the amount of labor, double the amount of capital, and double the reserves, then we'd be able to double production. We have constant returns to scale. Now, of course, there's a catch. And the catch is we're not free to just double reserves like that. That's something that the firm or the country is going to take as given. You can imagine doing extra discovery and exploration and trying to find larger reserves, but S is a natural resource which is renewable. So from another point of view, this doesn't look like a constant returns to scale production function at all. We have this thing, this S, which the country or firm takes as given. The reserves are in the ground, and you can't double them. You're free to change labor and capital, but sort of by construction, this alpha and beta are going to sum up to a number less than 1. And so if we have a fixed factor, if reserves S are a fixed factor of production, then this is a production function that exhibits what kind of returns? Yeah, diminishing returns to scale, exactly. And that's reflected in the sort of pictures we were drawing last time of firm supply. We had pictures of firm supply that looked like we have output prices. If we had a constant returns to scale production function, if alpha and beta were equal to 1, actually we can do this special example. If alpha and beta are equal to 1, what's the supply function look like? Actually, we can see it. We can read it down here if you want to plug it in quickly, or you might just remember. So if alpha and beta are equal to 1, then we have this stuff, but then we have S to the 1 minus alpha minus beta. So stocks no longer matter in that case, right? So if alpha plus beta are equal to 1, in fact, we are back to a constant returns to scale production function. Stocks, that's a world where the stock of the resource doesn't matter for production, and that's a world where, because it's constant returns to scale, the firm supply function is perfectly elastic. It'll just be flat. Okay, so this is the case where alpha plus beta are equal to 1. We also considered a special case last time where alpha plus beta were equal to 1/2. Does anyone remember what the firm supply function looked like in that case? We can sort of run it through here pretty quickly. If alpha and beta are equal to 1/2, then this thing turns into a 2. This is sort of the key part here. 1 over 1/2 is 2, minus 1 is 1/2. I'm sorry, is 1. So that gives us a supply function which has what sort of shape? Yes, Hillary. I'm sorry. You're reading out of this line? This is what I'm asking you about. So if one of... Oh, this factor here. And this is, I'm only caring about varying y right now, so I'm going to sort of keep this fixed for a moment. Right. So if we take alpha plus beta equal to 1/2, we get a 2 here. We get a exponent here of 1, and then this thing here turns into 1 over 1/2 or 2, which is maybe what you're asking about. Oh, I see. It's inverted because I made a mistake. Thanks. Okay, so that's, Jeff, would you mind giving Hillary 2 extra credit points? Thank you. Okay, all right, so setting this part aside, which we're not interested in anyway, Hillary's right to be the reciprocal of this. How does this thing vary with y? It's not a trick question. What should the inverse supply function here look like? Yeah, straight, and what's the intercept? If we set y equal to 0 in here, then price is equal to 0. So the firm supply function is going to pass to the origin. It's going to be a straight line with alpha plus beta equal to 1/2. What's the slope of this going to depend on? Yeah, it'll depend on the stock. It'll depend on the square of b, and it'll depend on these input factors. And this d, of course, remember, depends on the alpha and the beta. So, but b and s are going to be sort of key things that are going to be, supply shifters. So b, bi, si are supply shifters. What happens if we get a larger stock? If si goes up, what happens to the supply curve? Yeah, so si appears in the denominator of this. So if we get a bigger s, if s goes from 1 to 2, for example, that's going to change the slope of this from, it's going to affect it by a factor of 1/2. So if we get increase in s, we'll get a shift in supply, something like that. All right, is that sort of set up clear? Okay, I can never tell if you guys are bored. Sometimes I can tell. I can't tell right now if you're bored or confused. Anyone vote for bored? Anyone vote for confused? A number of people. Okay, so so what we're trying to do here, just to back up for a moment, is to describe the inverse supply function for firms with this kind of technology for producing oil. And I'm drawing a picture over here which tells us a little bit about how that supply is going to behave. It's a special case where we not only have this Cobb-Douglas reduction function, but also alpha and beta sum to 1. And the story I was told here is one where we've got a Marshallian supply curve that relates the amount that a firm is going to produce in relation to the prices they face. And we're talking about different things that will shift the supply curve. And one of those things is the size of the reserve that the firm of the country has. So according to that story, firms that have very large reserves, like Saudi Arabia at the very top of this table, should have supply curves let's consider the U.S. actually here for a moment. So the U.S. has very small reserves, actually the smallest reserves of any of the countries in this list. And so what should the slope of the U.S. supply curve look like compared to the slope of the Saudi Arabian supply curve? Should be considerably steeper. So maybe this might be Saudi Arabia, and this might be the U.S., something like that. All right. Now, SI isn't the only thing that affects the slope of this supply curve. What else affects the slope? This B, this technological parameter B. So maybe it's the case that the U.S. has better technology for extracting stuff than is deployed in Saudi Arabia. I'm a little bit skeptical of that because, again, the oil firms tend to be multinationals. But that's one possibility. Certainly, differences in technology across countries change the B. We can look at some countries here. Libya is a good example. Libya is a country which currently has reserves that are about 2.5 times the U.S. reserves. So you might think it would have a flatter slope for its inverse supply function. But for a variety of reasons, it has pretty antiquated oil production facilities. And so the technology that's used to extract its oil are certainly inferior to what's used in the U.S. or Saudi Arabia. And correspondingly, its production is fairly low. So this is Libya is a case of a country that has pretty decent reserves, has a low value of VI, is how we interpret this thing. And so its level of production is even lower than the U.S.'s, despite the fact that it faces the same world price. It's obviously below Saudi Arabia. So if we were to draw this in here, let me erase this middle one. If we were to add Libya to this graph, where would it lie relative to the U.S. and Saudi Arabia? Yeah, so if you're pointing this way. Yeah, that's right. It's producing less. So if a point like this is world prices, and world prices are about $100 per barrel now, then this pins down U.S. supply. U.S. supply right now per day is around 5.5 barrels. So this would be U.S. supply. I didn't draw this very well. Saudi Arabia would be supplying 8.9 out here. And we see that Libya is only producing 1.7 million barrels per day, or did in 2010. So it's back here someplace. So the slope of this line depends both on the stocks and also this DI. That's the takeaway from this. Okay. Any questions about this? Is that clear? Great. All right. So this is all stuff we did last time. This is really just a repeat of what we did last time, but I brought some more pictures for you. We also did something else just toward the very end of class, and that amounted to a couple criticisms of this supply function. And one of the criticisms that I'm going to try to address right now is that this production function allows countries to extract more than their reserves, which seems a little bit funny. So I proposed last time changing the production function to look like this, so that countries would face a production function like this. It's cheaper to take out a barrel of oil if you've got large reserves rather than small reserves, but that once you run out of reserves, once you've extracted amount Y, which is equal to SI, you have to stop. So there's a ceiling on the amount of oil you can extract, and it's just equal to the reserves you have. So this is just a small modification of the production function we talked about last time. I'll rewrite it here a little bit. So let's say that Y tilde sub I is equal to our old production function, BI times LI to the alpha, KI to the beta, SI to the 1 minus alpha minus beta. So I'm going to define this to be Y tilde. So this is the amount that firms would produce if they weren't constrained by the total amount of stocks they had. And then, this is just another way to write what we have up there, the actual amount that they'll extract, I'm going to call this actual production, we'll call Y. And that's simply equal to the minimum value of this quantity, Y tilde or SI. So they'd like to produce Y tilde, but they might run out of oil. If they run out of oil, they're going to be stuck in a corner and they can only produce this quantity SI. Okay. Is that story clear? All right, so if we have this kind of production function instead of this kind of production function, so we're going to impose the ceiling on extraction that depends on firm reserves, how would that change these inverse supply functions that we've been drawing? What's going to be different? Yeah, there's a max output, and you're drawing in the air with your arm exactly correctly. We've got output here on this axis, and so we'd expect if we're thinking about the U.S., for example, which remember has the smallest reserves of any of the countries we listed. In the U.S., the cost of extracting the oil up your reserve might be pretty low, but once you hit your maximum, say it's here, your supply function is going to stop. You can't produce more than your total reserves, so you're going to hit a ceiling. So you'll have a total supply function in this special example with alpha plus beta equal to 1/2, where you'll have something linear. The slope's going to depend on SI and BI. And then you're going to hit a kink, which only depends on SI, only depends on the reserves you've got, and then you can't produce any more beyond that. Yes? If you run out of reserves, why does the production stay at that level? Why wouldn't you get reserves? Well, remember, this is you're thinking of the second criticism of this sort of technology. So we're imagining that the world is born in the morning, firms extract a bunch of oil, and then we all die at the end of the day. So there's no all the reserves are just dumped in your lap, and you decide how much to use today, and then it's over. But if you were to use all your reserves by halfway through the day. Yeah, so you deliver your oil at the end of the day, so that timing doesn't become an issue in this artificial little static model. Yeah, no, but that's obviously silly in a way, but this model's static, so we can't really tell any sensible stories involving before you extract you have this much oil and after you extract you have this much oil. It all happens at once here. So we'll come back to a story maybe later today or maybe on Tuesday where time actually matters, where you extract oil and then later on you have less. Okay, so I want to take this model seriously, despite that serious defect. I think this model still has some value, and I want to take it seriously for a moment and draw sort of a more elaborate picture of this. This is going to challenge my artistic skills, but let's see how it goes. Actually, I think I want to do it over here. Okay. All right, so here's what I want to do. I want to think about this same problem we've been thinking about. That is drawing country-level production figures. Oh, and actually, I need to go back. Sorry, one slide here. That's not what I want. Okay, never mind. Okay, so let me stay there. Okay, so I want to go back to drawing a picture here of different countries' oil supply, and then what I want to do is, having drawn country-level oil supply for some selected countries, I'm not going to do it for all of them, I want to think about world supply of oil and how that aggregation works across different countries. Okay, so here's my plan. I'm going to draw a nice big picture here, so I'm going to try to fit several curves on it. And so this is total output, Y, of oil. Here are oil prices. And I want to make one more nod to reality that I haven't quite made, that I didn't make here, and that's that presently countries are producing oil already. We're not starting from zero. So to take Scott's thing, we're going to look at oil production starting halfway through the day or something like that. I know a couple of prices. I spent some time looking around for prices for the marginal cost of oil production for different countries, given current levels of production. And those data are problematic and not easy to find. If anyone can find better data, I'd be interested in hearing about it. But anyway, here are a couple numbers, some sort of rough ballparks. So for the U.S., the marginal cost of producing additional barrels of oil right now is about $15 per barrel. So given the fields that have already been developed, the stocks that are in the ground, the marginal cost is around $15. So that's an estimate of U.S. costs. Now, I'm going to continue to assume that we have a production function like this, with alpha plus beta equal to 1/2. And so the U.S. Production is going to look like a line here. The slope is going to depend on BI and SI, recall. Actually, I want to make this a little bit shorter. But there's going to be a limit to how much oil the U.S. can produce, and that's remaining reserves, which, and this is why I need my other slide, I think it was 19 billion barrels. Is that right? Thanks. Okay, so 19 billion barrels is the U.S. reserves. So this is going to go up to a point like this, and then it's going to go vertical. So this is the U.S. supply in this picture. Okay, a couple other countries here. Another country that produces a fair amount of oil is Kuwait. They have reserves that are about a third of Saudi Arabia's, but the marginal cost of extracting that oil is similar at present. And the estimate I've seen of that marginal cost is $4. So there's a lower marginal cost. This is meant to be about 1/3 of 15 here. So for Kuwait, it's got a marginal cost of $4. It's got total reserves of 102 billion barrels. So let's make this is 19. I don't know, I guess something like this might be Kuwait. So this is 102. And so Kuwait might look something like this. And then at this point, it's going to go vertical. If it produces this much, it'll be tapped out. Okay. Let me now add Saudi Arabia. Saudi Arabia's reserves are supposed to be 284 billion barrels, so roughly 3 times this. A little less than 3 times, something like this. So maybe this is Saudi Arabia. And what is it? 284, I think. Saudi Arabia has the same marginal cost right now per barrel that Kuwait has. It's got obviously larger reserves, so that may lower the increasing marginal cost. So it might have total reserves that do something like this. Okay, so that's Saudi Arabia. Sorry? Oh, yeah, thank you. Yeah, so Saudi Arabia and Kuwait. Okay, and I want to draw one more here. It's a country we talked about last time. So we considered Venezuela, which is supposed to have the world's largest reserves, 296. But its marginal cost of extracting this heavy crude oil is much, much higher than Saudi Arabia or the U.S. So I'm going to make up a number. This one's, I found sources for these. I didn't really find a Venezuelan one. This is what's completely made up. Let's suppose it's $50. And so in this case, we get a number for Venezuela that might look something like, something like this. Now, there's some, let me tell us, there's sort of 3 numbers that are pinning down each of the supply curves right now. There's the current marginal cost of extracting an extra barrel of oil. So I have some figures. I don't know how reliable they are, but I have some figures for the U.S., Saudi Arabia, and the rest of the Arabian Peninsula. I have a sense that the marginal cost of extracting oil, at least in the Orinoco belt in Venezuela, is several times higher than it is in the U.S. So that pins down this intercept. The other thing's a matter, of course, of the reserves, and we have some data on that. Again, this data may be problematical. There's political reasons to manipulate these, and they're uncertain and so on. But we do the best we can. There's a final number that's not pinned down, which I'm just sort of really freehanding here. It's the slope of the line from the intercept to the point where we hit the reserves. So let me wave my hands a little bit there. So we've talked about the slope of this thing. It should depend on SI, and it should depend on BI. In the case of Venezuela, even though the initial marginal cost is very high, it's got these vast reserves. And so the slope here is small because those reserves are very large. It might cost $50 to get out the first few million barrels of oil from the Orinoco belt in Venezuela, but it won't cost much more to take out the second million. So the slope is fairly low. In the U.S. case, I don't have a lot to say about the slope. Our reserves are small, which makes the slope large. On the other hand, we seem to be pretty good at efficiently extracting the declared reserves we have, so I don't know. Saudi Arabia is a case where they have tons of cheap oil they can extract. So this, again, is low because the slope is fairly low because the reserves are extensive in Saudi Arabia's case. And Kuwait, I'm just assuming because they have smaller reserves, they have a somewhat steeper slope. Okay. So anyway, but if you could tell with better data, you could nail down